Welcome everyone. So in our previous lecture, we learned how a signal can be amplified when it's passed through a BGT. So we found out when we apply an AC signal, which consists of a positive half cycle as well as a negative half cycle. So we have an AC signal as well as a DC signal. When we have an AC signal and as well as a DC signal, our total voltage, input voltage fluctuates between 2.1 volt to 1.3 volt. And therefore, we have a base current flowing into the uh, base terminal, which we found to have two component. One is DC, another is AC. So that means now, if the base component is changing, so which was something like that, so we found out something 25 plus 10 sine omega t. So that was our base current, which consists of two components. One is DC, another one is AC. DC component is DC IB, and the AC component we call it I. So we learned that if it is our total base current, and somehow if we know the value of the beta, in that case we can determine the total collector current, which is beta times 25 plus 10 sine omega t. So in that case we're going to find that the collector current is also changing with the time. So it has got two components, one is DC, another one is AC. And then since the collector current uh, is of this form, which consisting of a DC component as well as an AC component. So collector to emitter voltage VCE. So we found out that it is going to have, which is in fact VCC minus IC RC, whereas IC has two components. One is DC, another is. So again, so that means VC in fact is going to have two components. One is DC, another is AC. And finally, if we remove the DC component, so we found out at the output part for AC signal only, we have an output amplified signal. And this amplified signal is due to the input signal that we have applied, which is 0.4 sine omega t. So for 0.4 sine omega t, we obtained something like minus 2.6 sine omega t. So you see the amplitude is appropriately amplified. So at the input side, our amplitude is 0.4, and the output side, our amplitude is roughly minus 2.6. Now, one thing you should notice that that the output is 180-degree phase shifted. How is that? So when the input is positive, at the same instant, the corresponding output is negative. You see, the output appears to have opposite polarity, something like that. So input is positive, corresponding output is negative. So therefore, we introduce this minus sign, and we found out our gain AV, which is output divided by input, which we found out minus 2.6 divided by 0.4 sine omega t, and sine omega t, they cancel each other out. So that gives us roughly 7.6 point something, 6.5 times amplification. So that is how the amplification of any signal takes place when the BGT is operating in active region. Now, the one obvious question could come, why exactly we applied the DC voltage? So since we are dealing with only the AC signal, So that means we are applying AC signal, and all we are interested about from the output side is our also AC signal. So from AC signal to AC signal, and amplification of the signal is the important thing for us. Then why do we have to apply the DC voltage? Okay. So let's see why do we have to apply the DC voltage. So let's say, so the best way to explain this, if we try to analyze the amplifier without any DC voltage source. So let's say we didn't apply any DC voltage source, which means that as soon as the VBB, which was 1.7 volt source, was removed. So let's see what happened. It's removed. So the moment this voltage source is removed, you will find the AC signal that we are applying is dropped by 1.7 volt value. So that means it was previously it was fluctuating between 2.1 to 1.3. So now that we have removed the DC voltage source, so it is now fluctuating from 0.4 volt to minus 0.4 volt. Okay, so that means we no longer apply the DC voltage, we only apply the AC signal source. Now, so that means the voltage, remember that if you want to analyze the BGT, we have to first check the P side voltage with respect to N side voltage. Okay, so the base, it is an NPN BGT, so that means this is our P side and this is our N side. We said that whether the BGT is operating in active region or in saturation region or in cutoff region, the first thing that we need to check the voltage between P side and N side. So let's say when the voltage is maximum, which is 0.4, so our VP is equal to 0.4 volt, and in the N side voltage, since it is connected to ground, so we can say Vn is equal to 0. Now if we apply Vp minus Vn rule for the maximum voltage, which we're going to find 0.4 minus 0, which is 0.4, is clearly less than 0.7. Okay, so that when it is in a positive half cycle. On the other hand, when it goes to negative half cycle, so P side becomes even more negative. So that means our base emitter junction EBJ is always reverse bias. EBJ is always reverse bias. So that means on its own, the AC signal source keeps the emitter to base junction reverse bias. At the same time, if you find CBJ is also reverse bias, which is the case most of the time, so we're going to find emitter to base junction and collector to base junction, both of them are reverse bias. So if both of them are reverse bias, we know that the BGT is operating in cutoff region. Now we know if the BGT is operating in cutoff region, in that case, our base current is 0, our collector current is 0, our emitter current is 0. So if all the terminal current is 0, so if I want to determine VCE or the collector terminal, so it's that essentially we find, so VCE, which is measured with respect to ground, plus IC, RC equals to VCC. So since IC is equal to 0, so that gives us VCE or VC is in fact VCC. So let's say 10 volts. In our case, it was 10 volts. In our case, we're going to find regardless the value of the signal, whatever the value of the signal at the input, whether it is 0.4 or 0 or -4, the BGT is always in the cutoff region. If the BGT is always in the cutoff region, collector terminus voltage is always 10 volts. So that means we're going to find in that case VCE, collector emitter voltage, is always 10 volt. Okay, so for for any value of input signal, okay, VIT 0.4 to -0.4, we're going to find. So clearly the signal is not amplified, which means on its own the signal doesn't have the ability to amplify itself. It requires some support, and the support is provided by the DC voltage applied here. How does it do? So if you apply the DC voltage, you see our base current, DC base current is 25. Okay, right? And the signal is fluctuating between 10 volt to -10 volts. Now, what is the total voltage here? Now, if I again apply VP minus VN rule here, VP and VN rule for the total voltage consisting of AC signal source and DC voltage. And when we have both AC signal source and DC voltage, we can see the voltage is fluctuating between 2.1 to 1.3. Okay. Now, if I apply VP minus VN rule again for this range of voltage, so when VP is equal to 2.1 volt, so in case we have maximum voltage, the VN being connected to the ground, so VN is always 0. So in that case, we find VP minus VN, which is 2.1 minus 0, which is 2.1, which is 0.7. So that means for this value of voltage 2.1, we find EBJ forward bias. So let's check again with the lowest voltage, and lowest voltage occurs when Vi is equal to -4, so 1.3. So again, so let's say what is VP? VP is equal to 1.3 again. That is VN 0. So again, if I do VP minus VN, which is 1.3 minus 0, which is 1.3, greater than 0.7. So again, emitter to base junction is forward bias. So that means if you apply the DC voltage, you can always ensure that whatever the input, however small the input signal is, so it's make sure base to emitter junction is always forward bias. For both 2.1 volt it is forward bias, both 1.3 volt it is forward bias. So that DC voltage helps to keep the emitter to base junction always forward bias. Now that if it's always forward bias and if it is reverse bias, so the BGT is always in the active region. So we know that if BGT is always in the active region, only then you can use alpha and beta to determine the current. So that means if I know IB, I can determine IC as beta IB. So that means the current component in every terminal is linearly changing. Similarly, IE 1 plus beta IB. So this linearity in current relationship holds true only if the BGT is operating in active regions. So just to make sure the BGT is always operated in the active region, we have to apply the biasing voltage.